他们刚才的。好，我们再看第三种运动。So let's see another kind of motion. Okay, if you're using the fixed pendulum, you might have nothing to say why you have to use a polar coordinate. But if now analyzing a stretchy pendulum, then you have a very reason why you have to do so. So let's have a look.
Get this mass just right, and then I get this string just right, something weird happens. It bobs up and down, and then it stops bobbing up and down, it starts being a pendulum. And then it stops being a pendulum, it starts bobbing up and down. It goes back and forth between bobbing up and down and being a pendulum. This is called autoparametric resonance. It's where the energy from the spring is transferred to the energy of the pendulum, and then the energy of the pendulum is transferred back to the spring.
OK， 同学看到吗？所以这个不是一个简单的安排。好，下一个我们是来讲圆周运动。OK， 所以圆周运动的话，基本上你有一个你的曲力半径，然后你就算了你的速度。In the case when you have undergoing the circular motions, OK, the particle is going around a circle, so you can calculate the speed of circular motion as the perimeter of the circle divided by the period of the turn. Okay, and then next, okay, so where do we usually encounter them? You encounter them in the hammer throw. Okay, there is also a calculation of the centripetal accelerations. So previously we learned about, because when you go from A to B along the circular arc, the orientation or the direction of the speed is changing. So if the starting speed is VA, if you come to point B, it's also close to VA, if speed no change, then you still have a normal velocity change. Okay, the velocity change is in the normal direction. So then divided by time, then you got the expression of the centripetal acceleration being the v squared divided by the radius. So this is the calculation of centripetal acceleration. And then this is how you see it. Okay. So here you have a hammer throw. So let's have a look how to throw a hammer. 所以你丢铅球的话 ，OK。
In this video, we will look and learn at hammer turns and how they can generate speed with the hammer. Hammer turns generate further speed onto the hammer, more than just the swings in the delivery phase. You will reach a stage where no more distance can be achieved, so turns must be implied. Adding turns doesn't mean you forget anything you have learned so far, Everything will be important as you'll be joining all the stages together. As stated in our previous video, any throwing of the hammer implement must be done in the hammer case.
OK， 所以看到吗？所以丢铅球这个动作。OK， 丢铅球这个动作它涉及到的哪一些力 ？OK， in the case that when you are throwing a hammer by going around, so you have to have a tangential acceleration. Okay, this comes from tangential force. Okay, this force must be coming from the thrower. Okay, and then next, because it's going through a circular motion, there must be a centripetal acceleration. 所以你在丢铅球的过程中，你旋转的时候，为了给你的铅球加速，所以你在切线方向会给力。切线方向，铅球在切线方向有一个加速度，但因为你是转圈圈，铅球一直的方向会改变，所以你作用在铅球上应该有一个向心力 ，OK？ 那向心力就来自于这个丢手的这个拉力 ，OK？ 所以总的来说，作用在铅球上的力分两个部分，一个是切线方向，一个是向心方向，它的合力不会在你的圆周不平行于圆周，它会跟你的圆周做一个夹角。So in the case when you are throwing a hammer, the acceleration felt by the hammer has two components. One is tangential acceleration, the other is the normal or centripetal acceleration. So they add up to a total acceleration, which is offset from the tangential line of the circular arc. Okay? So the tangential acceleration is actually the tangential speed change over time. And then the normal accelerations is the speed square over radius. And what is your vector sum? Okay, 所以基本上这个就是你们上周小考的一个小题。OK， 不过这个要你画出来。所以上周小考同学也是有一个很大的缺陷是什么？你会写公式，但我叫你画图，要的就是画这个加速度向量图，不是画位移时间图。OK， 所以同学要记得 kinematic 的图，那你就要画速度向量或者加速度向量。OK， 所以一定要能画出来。OK， 小考的那道题已经算简单了，已经是单摆滑到最低点。如果说题目难一点，就会出单摆滑到45度角啊，那你的向量就会比较复杂。So you have to bear in mind that, okay, what you all calculated are all these vector. And then next, so we'll show you one example. In this example, you are basically throwing a ball, throwing a hammer in the horizontal plane. We now reduce the question to be 1D, 2D, okay, in the horizontal plane. You are given that the ball makes 2 revolutions per second. 2 revolutions per second is an RPM speed. How do you convert them into a period? A period is the time taken to finish 1 revolution. So in this case, this is 0.5 seconds. That's the period. And then next, for this hammer to go around a radius of 0.6 meter, how much is the speed? Okay, the speed is a perimeter of the circle divided by the period. 所以你在丢铅球转一圈的时候，请问铅球速度多少 ？OK， 那基本上就是铅球走一圈，它的圆周除以走一圈所花的时间，所以你算一下就是7.54米每秒。OK， 再下一个问题。So what's the next question? The next question is asking you, will you be able to find out what is the centripetal force so that you will keep the hammer to go around a circle? According to our learned formula, it is the mass times the centripetal acceleration, that is the speed square divided by radius. So it is equal to 0.5 times tangential speed square divided by radius, which is about 14 Newton. Okay, so that's the question. And then next, we come to another questions. Okay, what happens if I'm not throwing the hammer in the horizontal plane? If I'm holding a bucket with water, can I turn the bucket of water by a circle without the water falling down, okay, or pouring out?
Good morning. Today we are going to determine the minimum angular speed to spin a bucket in a vertical circle such that water will stay in the bucket.
Living physics.
Didn't we do this already?
Yeah, twice.
Actually, no. We have determined why water stays in the bucket and analyzed the situation generally. However, we have not solved this particular problem. Billy, could you please read the problem, and Bobby, could you please translate it?
What is the minimum angular speed necessary to keep water in a vertically revolving bucket? The rope radius is 0.77 meters.
Minimum angular speed equals question mark, and radius equals 0.77 meters. Bo, please solve the problem.
OK， 好，我们就是赶快大概看一下，讲完这个背景，基本上就是你的这桶水，你在转圈圈的时候，你如果慢慢转，拿了一桶水，慢慢转到你头上，结果会怎样？啊，你就变落汤鸡。OK， 所以你要转这桶水的话，你要快速转，要转到一定的速度，这个桶跟水在你头上，但是水不会倒下来。Okay, in this case, what's the minimum speed that you can keep the bucket of water upside down, but not pouring on your head? Okay, so you can see you might have one bucket with water. Okay, and then you bring them into a circular motion, and then the bucket will have the opening at the bottom, and then water over your head. How do you make sure the water don't fall down? Okay, there is very simple trick. Okay, we go straight to the point. Okay, because you are going through a circular motion, okay, with omega, okay, over a radius, then there is going to have a tangential speed r omega. Okay, if you come to that point, so what is the centripetal acceleration? The centripetal acceleration, let me write down, is going to be AC. So MAC is going to be equal to the sum of your forces. What is the forces acting on this bucket? Okay, you might have your tension to minimum if you are really going to fall down. Okay, so there are no tensions if it's falling down. Okay, you are talking to the level that tension is nearly zero at the critical point. Okay, all the weight is pointed downward. This is mg. Okay, so you're going to have the sum of the force that is equal to your mg. Okay, because mg is in the direction of acceleration, it's going to be positive. And if you have tension, tension must be, you can also pull it downward further. Okay? 所以在这个情况底下，这个你就可以找到，哎，你的速度最小值是多少？ Your minimum speed for not being pulled, okay, if tension is 0, then you're going to have mg times r divided by the mass as well. So in the end, you have the expression this is G square root of GR. 我们看一下，还是不是？哦，我是数。And then next, yeah, this is a minimum speed you can turn around. .好，同学看一下，所以你在不同的位置，你的这个受力会不一样。所以你是刚才是在这个最低位置跟最高位置 ，OK。所以你的张力，你如果要往下拉 ，OK， 它可以加强你的这个向心力。但是你如果是在最低位置，你的张力只能往上提。OK， 那就是还有另外一个数。So in short, what's the minimum speed that you can make sure the bucket of water don't fall down? Yeah, it is of this critical speed. 好，我们再来看下道题。下道题的话，我们拿另外一个情况。刚才是垂直转动，另外一个情况是在做三角锥的圆径转动。好。我们来看一下有没有什么道具。好，我们就弄了一个道具。OK， 拿这个包做单板。So this bag can be a normal pendulum. It swing in the same plane. Okay, you have analyzed this simple pendulum. And next, the other way of turning could be something like this, is it? So what's the trajectory of this pendulum? 来，先叙述一下这个动作。来，我们来叙述一下。来。好，我问你啊，我们找一下还没问过那个，来，我们问一下这个，来，刚才这个袋子做这个动作，你怎么叙述这个运动？一个几何形状，这个动作，锥形 ，OK， 所以这是三角锥，对的 ，OK。所以你在分析运动的时候，请把它的运动轨迹先画出来。So in the analysis of your motion, okay, if you are looking at the bag, it is go through a circular path, okay. But if you are looking at the string, it is going a straight line. So this looks like a cone shape. Okay? Then you realize that what gives you the tension is this string or your strap of your bag. And what is acting on the bag? Okay? It is the weight. Okay? And what is the motion? This motion, because it has a fixed radius and is going around it, then you can say I'm going through a circular motion. So in this circular motion at a constant speed, you have the radius and angular speed. At the same time, you have your centripetal acceleration. So meanings, if you are writing equation along the plane, if you are writing equation, I'm talking about centripetal accelerations in the plane, then they are center. Yeah. Then you should project the vertical force into centripetal force. This tension, let's say, is in the angle theta with respect to the vertical line. Then you're going to project, okay, depending on what you define. In this case, I define the angle to be what? This is theta. Then this one is, am I right? Okay, horizontal one is then T sine theta. So you see here, my centripetal force here is mg sine theta. Okay. Then if you are writing the equation, MAC is equal to the force sum, then there is only this tension sine theta. Apparently, you are not able to find the tension yet. So what can you write next? What can you write next is MAZ, the force in the vertical directions. What I'm very sure is because it's going through a plane motion. This is the Z direction. There aren't any Z speed. There aren't any Z acceleration. So AZ is equal to 0. But it does not stop me from summing up the force. What are the forces? Okay, the forces is the vertical component of your tension. Okay, this is your vertical component. Then it's going to be T cosine theta. And then what else? It's going to overcome the weight, minus mg. So in this way, in the second equation, you are able to find out what is the tension. The tension is the weight divided by cosine theta. And then if you know this tension in terms of the weight, then you can calculate back, and then you have the T times T sine theta equal to your mg sine theta divided by cosine theta. 所以同学看到没有？所以这个就是通过这个方式，你可以找到，通过角度你可以找到向心加速度。So there is a device developed using this principle. So look at here. 那我们来看一下这个当年的这个电影和野兽。OK， 所以要你看的不是这个影片的，我们要给你看的是刚才讲的这个 conical pendulum， 它基本上就是用来调节速度的。为什么？你通过你的这个角度，看到没有？我们刚才 m v square over r is equal to weight times tangent theta， 所以你的速度是什么？所以你的速度平方，我在速度，看到没有？你的速度基本上就是这个单摆锥形单摆的这个夹角，看到没有？
A centrifugal governor is a device used for controlling the speed at which a machine operates by regulating the admission of working fluid. Invented by James Watt in 1788, the governor became a fundamental component in many of the machines that drove the Industrial Revolution. Most commonly fitted on steam engines, power is supplied to the governor via a belt and flywheel connection with the engine's output shaft, causing the governor to spin as the engine runs. The governor operates the throttle valve, supplying steam to the cylinders. As it spins with greater speed, the centrifugal force acting on the fly balls causes them to move outwards and upwards against gravity, pulling the lever arms with them. As the lever arms flex, they pull down on a vertical shaft, lowering it into the throttle valve and reducing the gap through which the steam is fed. If the governor spins fast enough, the shaft cuts off the steam intake completely. The utilization of a
所以看到没有，你是可以通过离心力来做分析。看，我们再来看一下这题。OK， 这题做分析的时候很简单，它怎么分析呢？刚才讲的就是一个锥形一个三角锥单板。OK， 只不过现在是三角锥单板，这个是有两个质量。So in the case of the centrifugal governor, you have basically two mass. But in this analysis, we first analyze the motion in the Z direction. Okay, let's draw out the coordinate. So first, the free body we are consider is this end. What's the motion? This is your radial motion. It is going round. Then this is your circumferential. And it is going up. This is the Z. So you are describing the motion using a cylindrical coordinate. 所以在叙述这个旋转的这个离心速度计的时候 ，OK， 你用的坐标是什么？因为它是做一个三角锥运动，这质量是在三角锥的底盘，它会高会低，所以这个质量转圈圈，你就用 r 跟 θ 来叙述，高度的话就用 c， 所以你是用一个圆柱坐标来叙述这个运动。那我们来看一下第一个方程。So let's look at the first equation. In the first equation, what do you see? You have the z direction force summation. You are talking about z. Okay, what are the forces in the z direction? As we told you, you got tension with z component T. Okay, cosine 25 degrees. And then you have the weight. Because your z is upward, so you have this to be positive, weight to be negative. And if you are running at a constant speed, your z acceleration is 0. Okay? And then next, what else? So next, we'll consider the radius direction. Okay? Because you are turning around, then you have your centripetal acceleration that is toward the center. Then you have r θ dot square. And if you are going higher up, okay, it is possible that the radius will expand. Okay, so this is possible with the second term. And then next. In the theta directions, if you're running at a constant speed, then nothing. Okay, with this, you rearrange your equation, you finally find out how much is the tension. Your tension from the first equation is this ratio, and then how much the angle and the centripetal acceleration. If this is a constant speed, but then you can find what is the angular speed. The angular speed is basically this equation. 好，同学看到没有？所以这是一个例子。好，下面我们来再讲转圈圈。我们现在要讲的是压车，所以你在过一个转弯的时候 ，OK， 你压车，你靠的是什么？来，我们问一下，同学有骑车吗？来，前面3位男生。
这个手。
啊，来，骑车转弯怎么压车？
就不是骑车，就逆操作，就是 因为别人常常倾角。
倾角，所以力来自哪里？
惯性。
你确定？其实压车怎么动作？
我跨出去了。
你跨是脚跨还是什么跨？
任何人呢？
啊，所以这个压车，这个压下去这个力是哪里来的？
我给他的。
你的重力 ，OK， 可以。那下一个问题，那转圈圈的向心力来自哪里？来，问一下你好朋友。转圈圈向心力，他已经压车了。那转圈圈向心力是谁给的？摩擦力 ，OK， 那很有经验，可以多练习。然后我们看一下，来，这是重机压车 ，OK， 所以它是靠摩擦力 ，OK， 你要转弯的时候，你的轮胎要够宽 ，OK， 你用脚车的那个这么小的轮胎，这个转弯半径不会太小 ，OK。除非说你超低速 ，so next we get OK， 我们就不看这个，我们直接看。那巴士可不可以压车啊 ？OK， 巴士能不能压车？或者是有没有飞檐走壁的车？哎，你们这边有没有那种巡回那种特技表演的车？飞檐走壁的车，有没有看过？马戏团有 ，OK， 所以它是这样子，这个汽车才可以飞檐走壁。啊。啊，那个是机车 ，OK， 飞檐走壁，那吹过来。然后我们来看一下巴士怎么飞檐走壁。Okay. So in this case, we are looking at how a car can go nearly vertical walk. Okay. So let's have a watch of the video.
Ob Steilkurve, Schlechtwegstrecke oder steiles Gefälle. Auf der sogenannten Einfahrbahn testen Ingenieure Mercedes-Benz-Fahrzeuge auf Herz und Nieren. 6 Busfahrer aus dem Mercedes-Benz Omnibus-Fahrerclub sind heute eingeladen, einen seltenen und exklusiven Blick hinter die Kulissen zu werfen. Dann geht's los. Zunächst noch in gemäßigtem Tempo. Experten und Entwickler von Mercedes-Benz liefern Informationen aus erster Hand. Was ein Fahrzeug auf den verschiedenen Fahrbahnbelägen aushalten muss, bekommen die Gäste gleich selbst zu spüren. Nach 2 gemütlichen Runden wird es langsam ernst. Die Steilkurve rückt näher. Mit einer maximalen Querneigung von 90 Grad ermöglicht sich Schnellfahrerprobungen. Mit 100 Stundenkilometern geht es hinein. Die Fliehkräfte halten den Turismo-Car querkraftfrei in der Steilkurve. Der Fahrer kann sogar die Hände vom Steuer nehmen. Die Fahrgäste fühlen sich ein bisschen wie in der Achterbahn. Nicht allen ist die Steilkurve gut bekommen.
Eine Runde und also eine zweite schaffe ich nicht. Nee, schaffe ich nicht.
Auf der Einfahrbahn geht's in der Zwischenzeit weiter. Was es mit den verschiedenen Manövern auf sich hat, erklärt Andreas Türk, Entwickler bei Daimler Buses.
Wir haben hier mehrere Gefällstrecken. Auf diesen Gefällstrecken, wie der Name schon sagt, geht es nicht nur hoch, sondern auch runter. Mit dem Tourismus können wir locker ein Gefälle von 30% runterfahren. Wir haben auf der Geraden noch den sogenannten einfachen dynamischen Spurwechsel durchgeführt. Was sich jetzt so theoretisch anhört, ist nichts anderes als das schnelle Ausweichen vor einem Hindernis. Und wir haben hier subjektiv die Fahrwerkseigenschaften beurteilt. Wir haben dann noch die sogenannte kleine Steilkurve, die hat eine geringe Überhöhung. Auch die dient man grundsätzlich dazu, dass wir die Geschwindigkeit aufrechterhalten können. Wir können aber auch hier sehr eindrucksvoll demonstrieren, wie groß der Kippwinkel bei unseren Fahrzeugen ist. Das heißt, bei Schrägen von über 30 Grad
kippen die Fahrzeuge nicht, auch wenn man das erwarten würde aufgrund des vermeintlich hohen Schwerpunktes. Wir haben hier auf der Einfahrbahn auch noch mehrere Schlechtwegstrecken. Hier können wir in einem Zeitraffer den Lebenslauf eines Fahrzeuges darstellen. Das heißt, wir können Millionen von Kilometern zusammenraffen in wenige 1000 Kilometer, um dort den Verschleiß oder die Dauerhaltbarkeit festzustellen.
Nach zahllosen Runden geht die Fahrt zu Ende.
Hervorragend. Oh, toll. Ganz einfach toll. Hat total Spaß gebracht. Also kann ich den ganzen Tag machen. So.
Das ist alles beeindruckend gewesen. Sei es die Hobelstrecke, sei es das Driften, was er gemacht hat mit dem Fahrzeug, das ist natürlich...
Die Geschichte des Sterns wird hier lebendig.
好，那我们来看一下这个客运怎么爬墙的，或者是这个汽车。So in this case, we are going to analyze how a car going through a corner with a bang. Okay. This is what you call a bank turn. Okay, bank turn is quite common, not just for car, also for all kind of vehicle. Let's draw that out. Okay, imagine if you now have a slope with a bank angle theta. On top of that, you have a car. Okay, with a wheel. Okay. So here, imagine the center of gravity is at somewhere here, okay? So what helped you to do the bank turn, okay? So if going round a circle, okay? Just now we tell you before, if there is no bank angle, if car is sitting on its on way, okay? If you want to go around a circle, there must be a centripetal acceleration. Okay? Or you can write nv squared over the radius. What gives you this force? Okay? It must be coming from the friction force. Okay, 你有4条轮子，那就是4个侧向的摩擦力。OK， 你如果是纯粹，就是在平地上 ，OK， 那跟你刚才压车不一样。压车的话，压车有提供向心吗？有提供向心力吗？刚才压车同学，有提供向心力吗？在平地上。好像没有，对的，那就是靠轮胎嘛，跟你轮胎越粗越好，在平地上。但是刚才看到例子是不一样。So what you see just now was there is a bank， 有一个岸边，然后看比较斜的。所以这个时候，来我们来问看同学，重力还是一样向下。那谁来提供你压车的力？来，我们来黑色口哨的同学，来，作用在这辆车会有什么力？摩擦力一个 ，OK。那还有什么力？正向力 ，OK。好，我们再画正向力，这可以。好，那谁提供向心力？ OK， 正向，当然摩擦也有 ，OK， 不过主要是正向。So in this analysis, you can see that there are a few forces acting on the car, running on the bank. There are weight acting on the car. There are normal force acting on the wheel of the car. There are friction force acting on the wheel of the car. If now you want to write the centripetal force sum, okay? This is your radius, this is your centripetal force direction. So this can be written as V squared over R, okay? So in this case, what are the forces in this bend direction? You can do the projection. So if this is a slope angle theta, this is your theta. If I do the slope here, this is my theta. What's it? What else? This is my theta. So what are the force component? If this is my normal force component, I can either, okay, how can I write it? What's the normal force? Okay, it's going to be, is it theta? Let me draw out again. Okay, the definition of the slope, let's see. This is the slope theta. This is a normal force n. Okay? If I'm going to draw horizontal component, this is my theta, and this is my theta. Okay? 所以同学看过了，啊，这个画错了，这个在哪里画错了？要把这个裁掉错了。This is your theta. Okay? So one of the force is normal force sine theta. Okay? Of course, if there is a friction, let's draw about the friction. Okay, you draw a slope. There is a friction. And you want to find the horizontal component. This is a friction force cosine theta. So in this way you can do the analysis. So here people only tell you about normal force, but in reality your car wheel does have the friction component. So in this way, when you're writing which give you the normal force, okay? So bear in mind, it's not the so-called normal force per se. It's actually the centripetal force. Because, not to confuse you, since you define normal force to be vertical to the plane, you better rewrite this. This is not the normal per normal. Okay, we are talking about centripetal. So, 所以通过这个方式，我们就可以找到你的。Okay, how much of bang angle it can support you? Okay, it depends on the speed. If you need a greater speed, okay, your angle will go much higher. Okay, 所以好，我们就拿一个例题来讲，就是说，你如果转弯半径是50米，这个转动速度为50公里每小时，基本上是14米每秒。那么你的这个 bang angle 单纯就是靠你的重力来给予你向心力，那基本上这个 bang angle 的这个 bang 角度应该是0.4 radian，0.4 radian 基本上是22度。Okay. So in this case, so we are able to analyze how much the bang angle needed. Okay, to keep you turning a corner without the need of friction. Okay, so this is well exceeding your friction. Okay, 好，看到我们 OK， 今天就上到这里。OK， 然后我们之后再讲。好，谢谢。 Tschüss.